Good morning, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm the host for today's presentation. And today the topic is how to evaluate and mitigate transferred voltage hazards using the XGSLab product. And before I introduce our speaker for today, I wanted to briefly talk about a little bit of a background here for those of you that haven't joined us before. For almost 5 years now, EasyPower has been the North American partner for Cent Ingenieria products, which is XGSLab, is one of the most powerful software packages on the market for electromagnetic simulation for power, grounding, and lightning protection systems. And it's the only software on the market that accounts for all three standards in use today around the world. The presentation has been recorded previously, and I'll be playing the video. This will permit our guest speaker to be online live, and so by all means submit questions during the presentation using the question box, but we will have a short Q&A session afterwards, so by all means take advantage of this resource. Mr. David Lewis is a professional engineer who is specialized in electrical studies for power transmission and distribution system analysis. He has valuable experience in various infrastructure studies, including substations and facility grounding studies, AC electromagnetic interference studies, and today is responsible for training and support in the use of XGSLab for these studies. And we appreciate you attending today.
Hello everyone, my name is David Lewis and I work with EasyPower. Today I am presenting the evaluation and mitigation of transfer voltage hazards. In this presentation, or really the purpose of this webinar, is to promote the study and mitigation of transfer voltage hazards. So at the end of this presentation, it's my hope that you'll be able to define what a transfer voltage is, identify scenarios that could be transfer voltage hazards, and be able to recommend some approaches to evaluating and mitigating these types of risks. So when we're going through this webinar today, really I want to highlight some situations and thoughts you should consider when you're doing a grounding system analysis and possibly a transfer voltage analysis. This isn't necessarily going to teach you everything that there is about transfer voltage scenarios because there's just a whole world out there. But when we want, what we really want to do is just provide some additional information to elevate some of the industry knowledge and kind of get some of the people that are listening to this webinar and understand their perspective for situations they have seen. So when I'm doing this presentation, please feel free to write questions or make a comment as you think of it, and we'll be sure to address them either at the end of this presentation or get back to you. So with that, let me kind of go over our outline of how we're going to accomplish our goals for this presentation. So I want to make sure everyone's on the same page, at least for grounding analysis. So we're going to talk about some of the grounding basics. Then I want to define what a transfer voltage is. We'll highlight some examples of what a transfer voltage may look like in the real world and discuss some of the challenges that occur when you're trying to evaluate transfer voltages. We'll provide some mitigation strategies for resolving transfer voltage issues and go over a couple case studies of how to implement mitigation properly and one that's showing how you could improperly implement some mitigation strategies. So with that, let's first talk about some grounding basics. So the reason why we do grounding or we're grounding equipment is that it allows for that equipment to operate properly under normal and fault conditions. Grounding provides protection from surge and lightning effects, and it provides personal protection under fault conditions. And when we're doing a grounding system analysis, this last bullet point is primarily what we're looking at because that personal aspect is usually the driving factor for our grounding system design. So some of the concepts associated with a grounding study is we are looking at a ground fault or earth current going through your grounding system. And what that does, whenever you have a current, there's a voltage, and we see a ground potential rise at your grounding system. And you can see that illustrated on the right here. We have the voltage potential of the soil illustrated, and you can see approximately 1,800 volts is where we see the peak of this ground potential rise, and that's a voltage relative to some remote point on Earth. And when you have very large systems, or really normal size grounding systems, there's always going to be these peaks and troughs. And what these do is that we're trying to make an equipotential plane, but because we will always have some sort of voltage drop in the soil as it propagates through that soil, we have potential differences that could be hazardous. What we look at in a grounding study are our touch voltages and our step voltages, and these are usually what we look at for determining personnel safety. So on the left, I have an illustration of a system or a piece of equipment that's received a fault, and that equipment is elevated to 1,000 volts. An individual is in contact with that piece of equipment. Their reach distance usually approximated to about 3 feet or 1 meter, and that distance between their hand and where their body is located and their feet on the soil creates a voltage potential difference between their hand and their feet. So in this situation, because of how the voltage propagates in the soil, the individual is standing where the potential at their feet is approximately 800 volts, while the potential at their hand is 1,000 volts. We would call this a 200 volt touch potential, and this voltage difference is what we look at. Similarly, we have a step voltage concern. In this situation, an individual is not in contact with any piece of grounded equipment, but they're simply in contact with the soil. And because of their stride length, they have a different potential from one foot to the other. And in the illustration, we have one foot that's at 900 volts, the next foot at 800 volts. And so this is what we would call a 100 volt step potential. Now, when you're doing a typical grounding analysis, you would evaluate touch voltages where equipment can be touched. And step voltages obviously are within a given area. You don't have to be touching a piece of equipment. And what I'll talk about in this webinar is generally referring to the compliance criteria associated with IEEE Standard 80, which is the personal protective standard for substation grounding. So now we have a little bit of a basis. We can start to define transferred voltages. So a transfer voltage is a unique or special sort of touch voltage scenario where we are having voltages either transfer out of a substation or grounding system to an external point, or it's being transferred in. And you could have this either as a direct metallic conduction or a conduction that is through the soil. And you'll be able to see this as we step through some of our identifications in the next slides. So here we have an example of a substation fence on the right. You can see it has a little danger warning label here. And there is a little panel that's providing physical security to a client's site. And then we have some barbed wire that continues on to another fence. And this is owned by the adjacent facility or the adjacent landowners. And you can see here that it appears that somebody has taken some steps in order to avoid a direct metallic conduction of a transferred voltage. The substation fence, which are grounded and bonded, um, this post, there's an air gap between this post and the post on the right. And what that suggests is that somebody was doing a design and considered direct metallic transfer voltage and tried to mitigate for that by providing this little air gap. Now, this appears to be a proactive step in mitigating any sort of direct metallic conduction of a voltage from the substation to this neighbor's fence. But when you look closely, you can see on the bottom left-hand side, there's actually a ground lead that's been connected to this fence post. And I think this could have been something that was implemented by an engineer, um, expecting that they were fixing the design, or it could have been implemented by the field crew, not understanding that the typical operations for grounding a body of the substation fence will actually produce a greater hazard for the personnel and public if you're grounding this external fence and transferring voltages directly through the metal of the fence. And this really highlights why we're doing this webinar today. Another type of issue we see is substation to substation transferred voltage. Often when we're doing a grounding system analysis, we look at a substation's grounding system in an isolated view. And the reason is that this would often produce a more conservative result because the smaller grounding system can have a higher grid impedance and therefore you can have higher ground potential rise. When you have systems that are relatively close to each other and those systems have different voltage levels and different fault current availabilities, then that isolated view of the substation is really no longer necessarily conservative. And you may actually be overlooking some transferred voltage hazards from a system that has a higher fault current availability. Another type of system or recipient that we see often is a pipeline. So pipelines require personnel to go out often to check meters or um, do some testing on their test leads, and that personnel is required to be in contact with the pipeline on a regular basis. And if a fault were to occur, you could have substantial voltage transferred onto the pipeline through conduction of the soil. And the challenge with that is because those pipelines have a dielectric coating often, that coating can maintain transfer voltages extending out hundreds or thousands of feet away from the substation or away from the source of the fault current in this transfer voltage. Finally, I just wanted to mention another type of recipient we could look at, and this is really a facility. Um, and it's important to note that in some manufacturing facilities, there can have equipment that's very sensitive to ground potential rise. And in an instant during the manufacturing process, if that's interrupted, that could cost them hundreds of thousands or millions of dollars in the instant that a fault occurs if we're not being cognizant of that sensitive equipment for our ground potential rise and transfer voltage issues. So how do we actually resolve these transfer voltage challenges? So first I want to talk about some of the considerations when you're looking at this. We need to understand what we need to evaluate for transfer voltage hazards. Um, Maybe we're looking at pipelines or fences that are within a certain distance or within a radius of our system based off the ground potential rise. When we identify affected parties or affected recipients, we need to determine if they're internal and um, work with our internal team to mitigate those transfer voltage hazards or get in contact with the external owners. And whenever you have these types of interactions between different industries, there's often a lot of room for miscommunication to occur. So there needs to be upfront conversations on what are applicable limits for evaluations for the given recipient, whether it's a pipeline, a fence, or some other sort of metallic system, and who's actually going to be providing the services to determine the um mitigation strategies and the hazards that may exist on site, and possibly testing afterwards. And of course, whether you have a fully internal recipient or external owners, whatever mitigation strategy that is arrived at has to be agreeable to those that are actually working on these systems and has to be something that is actually able to be installed. So you can come up with a great engineering design that may not be able to be physically installed. That's not a great system to resolve transfer voltage hazards. Or if there's a process that has to be developed in order to mitigate transfer voltage hazards, it may be more challenging to actually create that training for personnel and may not be applicable for the public. So let's talk about some mitigation strategies of how we actually um, design systems to mitigate transfer voltages. So first we can look at mitigation strategies internal to a grounding system or to a substation. We can add more grounding, and what this does is that it can reduce our grid impedance and reduce our ground potential rise. And this gives us a lot of control of our design, and it's just like doing a normal grounding system analysis. It has a lot of advantages in that way. Another approach is that you could provide non-conductive fencing. So if you're having a direct metallic conduction, you could have an option to replace your fence with a non-conductive alternative. And it doesn't necessarily have to be around the entire exterior of the fence of your substation. Um, it could just be along the section that's affected or directly connected to the recipient fence or structure. Another option to consider is either disconnecting or connecting your shield wires or neutrals. And this one is um, what you can do when you connect a shield wire or distribution is that you can lower your ground potential rise at your grounding system. And that's a benefit for reducing transfer voltage hazards. However, by connecting those shield wires or neutrals, you're also transferring voltages out to more locations at the base of your towers and poles. So I think regardless of what strategy you're choosing, there's additional concerns to think about how you're introducing a solution that could be introducing a new hazard or new problem. So those were strategies internal to a grounding system or a substation. Some strategies external to a substation, obviously we can include non-conductive barriers. If we are able to control access to a object that's that has receives transfer voltages, we can eliminate those risks. We can also look at gradient control mats. And what this does, as you can see on the right, we have a pipe and below it is a mesh of metal. And this provides an equal potential plane for an individual's feet to be standing on when they are touching the pipe or another object. They will have their hand and their feet at the same potential, thus they're not going to be receiving a touch voltage hazard. One thing to note though, when you use gradient mats is that there's always going to be an edge, and on those sharp edges, you can create step voltage potentials. So that's something to look at, again, noting that you're fixing one issue but possibly creating another one. You can also ground the recipient, whether you're trying to ground the recipient to elevate its voltage or ground the recipient to reduce its voltage. Um, the overall goal is trying to remove or reduce the voltage difference between the object that has received the transfer voltage and the public or personnel that could be contacting with it. Another option is personal protective equipment. And again, this goes back to the previous slide where we're talking about agreeable options. When we're looking at PPE, there may be new processes that need to be incorporated, or maybe not. This has to be something that's evaluated by the personnel that are working on the affected system. And if it's in a situation or a location that's easily accessible by the public, PPE may not be a valid option to consider. So let's go into some case studies. And for this one, next few, I'm going to talk about um, fence as our main recipient. So this first slide demonstrates a relatively uh, more simple transfer voltage hazard to resolve. On the left-hand side, we have a substation, and during a fault, we have a voltage that's transferred out along a neighbor fence. And green is indicative of touch voltages that are below the compliance limits for IEEE standard 80. Yellow denotes locations where we are exceeding touch voltage limits for personnel. So we can see during a fault at that station, we have substantial enough voltage that's transferred to this neighbor fence to create a touch voltage hazard. We can mitigate this by using possibly a single non-conductive fence panel or creating some sort of air gap between the substation fence and the neighbor fence. Just by providing that little gap, we're no longer directly metallically conducting any sort of voltages. We are now seeing that our neighbor fence no longer exceeds touch voltage limits, and we've mitigated our transfer voltage hazard. A more challenging situation with a neighbor fence is when we start to see touch voltage hazards that develop through the conduction through soil. So we have the same station here. I've elevated the fault current or the energization, and we have that neighbor fence not directly connected to our substation fence anymore, but it's approximately 20 feet outside the station. So during a fault, what we see is we have a ground potential rise, and that's drastically elevated in this extension of our substation grounding system. And that drastic elevation of the ground potential rise results in a touch voltage hazard in this yellow region of the fence line. Now, an interesting trend is if you go from left to right, where don't have sufficient voltage along the fence line that it would exceed touch voltages until we get to this extension. And then we hit a point where our voltage of the soil and the voltage that was conducted onto the fence are actually close enough that they're no longer exceeding our touch voltage limits. And you can see another illustration of this. The green line represents our ground potential rise of the soil, and the red line represents the touch voltage of or to that external fence. And this red dashed line represents our touch voltage limit. And we can see when the ground potential rise, as it starts to reduce as we leave the substation, our touch voltage to that fence drops to nearly zero at the point where the voltage of the metal, the voltage of that fence metal is approximately equal to the ground potential rise or that voltage on the soil right in this green area. The problem is now, as we go farther to the east is that our fence now has an elevated voltage and our ground potential rise from the substation is dropping off. So our fence is now a sufficiently high voltage that it's creating a touch voltage extending out from our station. Now we can apply the same sort of mitigation that we saw earlier. It's just we don't have a single break in our neighbor's fence. We now apply multiple breaks or multiple non-conductive panels in order to mitigate transfer voltage hazards. Here you can see there's a break that really isolates the fence section that is closest to the substation grounding system. And it extends out multiple panels to reduce the conduction to the outer fence line. And here we can see by using non-conductive fence panels, we're able to have our compliance for touch voltage met in multiple locations. So in this central fence section where we're still using that steel fence, we have the soil at the person's feet is at the same potential or relatively close potential to the fence itself. And we can see that on the left and right hand side. So another case I want to talk about, or another recipient, are pipelines. So here's an image of a substation with an adjacent station, and they're connected, and between them runs a pipeline. And what I've done here is I've plotted our ground potential rise contour, and I have the 330 volt contour plotted right here, and I have my pipeline voltage, which is approximately 80 volts. Now the reason I'm plotting the 330 volt contour is that my touch voltage, the compliance limit for that over native soil, is approximately 250 volts. So noting the difference between the pipeline and the soil, I will know that any appurtenance for this pipeline within my 330 volt contour could result in hazardous touch voltages. That same pipeline or that same system illustrated here, I have our green indications on 4 pipeline appurtenances, and you can see 3 of these systems where the personnel are working on the pipeline exceed touch voltage limits. And then our 4th one that's extending off to the east is within compliance for IEEE standard 80. Those the limits for IEEE standard 80. And we still have our pipeline at 80 volts. Now I want to go through a couple strategies here. And our first strategy is going to not be effective. So one approach for mitigating transfer voltage is grounding the recipient. And when you're grounding the recipient, you have to be cognizant of your location and that location's ground potential rise, or the potential of the soil in that location. So if I add grounding on either side of the pipeline between my substation, what it's doing is it's actually elevating the pipeline voltage significantly. Previously, we had a pipeline voltage of 80 volts, and now we can see we've actually elevated the pipeline voltage closer to 500 volts. And our appurtenance that was well off and good on the right-hand side is no longer compliant. We are exceeding touch voltage limits on the right. This mitigation strategy was not effective for our appurtenance in the middle. Interestingly enough, our 2 objects on the left-hand side of the pipeline, there's a reduction in the voltage difference between a person's feet and the pipeline now that we've elevated the pipeline closer to the ground potential rise in these areas. But noting my 250 volt limit over native soil, this pipeline can carry this voltage for hundreds or thousands of feet, and having a pipeline voltage of 500 volts means that we need to ground it somewhere sufficiently far away to reduce that transferred voltage. So I've now created a much worse condition extending farther away from my initial base case. So a better method we could use is a gradient control type of method for these pipeline appurtenances. So we can see each of the 4 locations now shows a green indicator, indicating that our touch voltages no longer exceed the compliance limits. And we do elevate our pipeline voltage up to 160 volts just by adding primarily these 2 or 3 gradient control mats. It's picking up that voltage the uh, from the grounding system. So you're transferring more to your pipeline, but it's not exceeding the 250 volt compliance limit over native soil. So overall, we're seeing a net benefit. We've reduced the amount of mitigation we need, and it's mitigation that is highly effective in the regions where we've placed it. So in conclusion, what I want to go over is that transfer voltage concerns are approachable. They look like fences outside of a grounding system or pipelines or other metallic paths. You can use the tools that you use for typical grounding system analysis in order to mitigate transfer voltage hazards. You have to know if you're using a grounding software, whether it's assuming an equipotential plane or if it's actually evaluating the self and mutual impedances like XGSLab does. You also have to note that when you're evaluating a system, you can start taking a look at various types of recipients like pipelines or fences and considering those for transfer voltage mitigation. Or maybe a system that is exceeding a certain ground potential rise or has a long fault clearing time. Those types of systems may be appropriate to look at for transfer voltage hazards. Overall, what we want to do is try and produce a system that is going to result in the least amount of hazard. Um, so at this point, I think I'd like to turn over to answering some of the questions.
Okay, so we had a few questions going through the webinar. Before I jump on those, though, I just want to make a note I had help in developing this presentation from my colleague Andrea Wood over at Power Engineers. So just wanted to thank her for her support in developing this. So going through the webinar, we had a couple questions about ground potential rise and the relationship to safety and limitations of ground potential rise. So when we're looking at touch and step voltage potentials, we're looking at the difference of a system from one point to another, whether that's between an individual's feet and their stride length, or if it's between an individual's hand and their feet. So there's not necessarily a limit for a potential that a person could be placed upon, but there's a limit to how much difference that person can withstand. And there are codes and limits for some equipment, and that comes from really the ability of that equipment's insulation to withstand the voltage potential difference that might be on a cable sheath. So there's not necessarily like a GPR limit for a site, but there are limits for a personal safety aspect, but there are limits for equipment. Another question we had was, in this presentation, we used some non-conductive fence in order to resolve some of the transfer voltage issues. And the way that was implemented in the case studies was simply by deleting or removing the conductive portion of my fence from the model. And that's just a quick way to remove that, because a non-conductive fence is not going to have any sort of electrical participation in the system's model. But you could also illustrate that or show those continuation of the fence visually in XGS by using what we'll call a background image. So that way it's visually represented for whomever is receiving a report of your transfer voltage analysis. It shows as a continuous fence, but there's obviously a difference between the conductive portion of that fence and the non-conductive portion. Another thing I want to get or clarify on is at the end of this webinar, I made a note about the equipotential plane assumption. So there's hand calculation methods that allow people to do really grounding system analysis using an Excel sheet or piece of paper and a pencil. They're great for simple applications, and the way that those are allowed to, you're able to do that sort of calculation is that it makes an assumption that your entire grounding system is at the same voltage potential. So if I have a system that is 1 ohm and I have a 1,000 amp fault current, then I have 1,000 volt potential on that grounding system. Now, the equipotential plane assumption makes that 1,000 volts propagate everywhere, but in reality, if you energize one far corner of a system, there's a voltage drop through the soil and through that metallic conductor from one corner of your grounding system to another. Now, if you think about that being modeled, that's what XGSLab will do, is it models that voltage drop. Some more simple applications may not model that voltage drop. And if you have a fence line extending out 200 feet in a linear path, you're going to hold that 1,000 volts through that entire linear path, which isn't representative of the actual physical effect that would happen in the real world, and is going to give you a false sense of your results. And in that particular example, it's going to give you worse results than you would really see in the real world. It's also possible, though, that you could actually have that equipotential plane play out in your favor as far as its grounding design, and come up with a design that actually does not mitigate your transfer voltage concerns in the real world because of that equipotential plane assumption. So it's just something to note when if you're evaluating software or doing hand calculations, that is something that's taken into account. I think I addressed most of the questions that are coming up. Obviously, if you think of a question, you have my contact information on this slide, so feel free to email or give me a call anytime about grounding questions, AC interference questions, lightning, or XGSLab. Certainly appreciate the opportunity to talk with you all today.